In this example, we look at a shear. So suppose we've got an operator on F2, and it's given by sending the point xy to x plus ay y for some fixed scalar a non-zero. Okay. Then let's see. T of x comma 0 is going to be x comma 0. So lambda equals 1 is an eigenvalue. And the x-axis, or the first coordinate, is going to be an invariant subspace. And meanwhile, if we look at points of the set, I'll call it WC, and by WC I mean the slice at C, so all points of the form T comma C, where T ranges through F, and and C is fixed. So if we look at the action of T on this set here, WC, then T of W is going to be, so T of T comma C, which by the definition of the operator is going to be T plus AC comma C. This is going to be back in WC again. So WC is invariant, but it's an invariant subset because it doesn't pass through the origin. It only passes through the origin when C is equal to 0. And in that case, it's actually just U that we're looking at again. All right. So the picture that we've got in this situation is, let's see, something like this. I'll just do it for, oh, come on, give me my straight line. There we go, boing. So I'll look at R2, so this is the case when F is equal to R, because then I can actually draw it. And suppose that A is this one right here. And then if I look at this, so suppose this is at height 1 on the vertical axis, then oh, come on. Well, my little auto straightener is not working for me today, so oh well. There we go. Okay, so that's showing how much a point gets moved. So the vector that started here at 1 got shifted over there to A. If I were to look at some other point up here, C, then this line across here is going to be my WC, and the action of T is going to move it to the side here over to this point right here, which, and let me get my dumb label out of the way, would correspond to this point here, A times C. So that's what this transformation is doing to F2. And so to see that this is the only, I guess, let me say non-trivial invariant subspace, because of course we know that the zero subspace and F2 itself will always be invariant. Suppose that F2 were actually equal to a direct sum of U and V, where W is invariant. Okay, so then the dimension of W would have to be the dimension of F2 minus the dimension of U, which is 2 minus 1, which is 1. So we'd be on the lookout for a one-dimensional subspace. So any element of W would be an eigenvector. Right, that one-dimensional subspace is going to look like all scalar multiples of some eigenvector. But if we look at the equation TW equals lambda W, then on the left side, by the definition of our operator, we have T plus ACC for whatever point T comma C we've chosen. And then on the right, we have, actually, here, in order to make it look more like what we started with, let me go back to the notation x plus AY comma Y. And then on the left, if our W is x comma Y, we're going to have lambda x, lambda Y. Right? And so if these two guys are equal, then what do we see? Well, comparing the first coordinates, we get x plus AY equals lambda x. And comparing the second coordinates, we get y equals y lambda. And so from the second one there, we have that lambda equals 1 or y equals 0. But if y is equal to 0, then we start off with a point back in that invariant subspace that we looked at the beginning on the x-axis. So we're looking at lambda equals 1, but then putting that one into the first equation, then we see that x plus AY equals x, which implies AY equals 0, which implies a equals 0 or y equals 0, but we started off by saying a is not 0. So then w turns out to be back in u in any case. And so the moral of this story is that U is the only invariant subspace for this example.